In the last session, we looked at the first topic in periodicity, and we looked at the periodic table as a whole. What we're going to do today is we're going to focus on a particular area of that periodic table. Now, historically at GCSE, you would have looked at groups. So you would have looked at group 1, you would have looked at transition elements, and you looked at group 7 as well. What we're going to do here is we're actually going to look at a period. Remember, a period crosses the group, so it goes from left to right of the periodic table. And the period that we're going to look at today is period 3. So that's our focus today. We're going to look at period 3. Now, the name of this topic is actually periodicity. Now, the word periodicity actually means regularly recurring. That's what that actually means. So it's all to do with the regularly recurring patterns within period 3. And that's what we're going to do today. Now, let's just recap what is actually period 3. So period 3 is the third line down, if you like. Remember, period 1 has got hydrogen and helium in it. Don't forget, that is period 1. Period 2 starts with lithium and ends with neon. And we're going to look at period 3 today. So that is sodium, magnesium, aluminium, silicon, phosphorus, sulfur, chlorine, and argon. Please bear with me today. I'm going to use, a lot of the time I'm going to use the symbols instead of writing the names of the elements. It's a much quicker process, and it's easier for you guys to take notes as well. So we're going to look at the trends and properties of those elements, and the one that we're going to really focus on today is the melting points and boiling points of these elements. So first of all, what we're going to do is we're just going to recap some basic concepts from your topic 3 and then build on that. So topic 3 is all about bonding, isn't it? So we know that these 3 here, sodium, magnesium and aluminium, are giant metallic. So if I use the term giant metallic for those 3 elements in this video, then you know what that is. So giant metallic. Silicon is what we call giant covalent. Sometimes you would call that macromolecular. That means exactly the same thing. Macro means big, and molecular obviously means molecule. So macromolecular means big molecule. Silicon forms a big molecule, just like the element above silicon in the periodic table. So silicon's the period 3 element. The element above silicon in the periodic table is carbon. Carbon is also a giant covalent substance. And you look at carbon in a bit more detail in topic 3, which you would have already done. And that, of course, is a macromolecular molecule as well. So a diamond is a macromolecule. So that's that one. Then you've got these ones here. These ones, those 3, are simple molecules. Simple in this case just means small. Remember, argon can't be a simple molecule. So please don't say that argon is a simple molecule. It's not a molecule because there's only one atom in argon. These have got more than one atom. You'd already know that chlorine is Cl2, but we're going to look at phosphorus and sulfur within this session as well. Argon is just atomic. Now, you might have heard the expression diatomic. In this case, it's monatomic. Okay. Okay, now, hopefully we know the structure of sodium. We've got sodium ions there surrounded by delocalized electrons. Magnesium 2+ ions surrounded by delocalized electrons. Aluminium 3+ ions surrounded by delocalized electrons. Silicon, however, is a giant covalent substance, so all of the silicon atoms are chemically bonded to each other by covalent bonds, simple single covalent bonds. In phosphorus, we will write this down in a second, don't worry about it, but phosphorus is a covalent substance again. It's simple molecular. It might be useful for me to write the word covalent under there for you. So that's actually P4. We'll draw that structure in a second. Sulfur is actually S8, and of course chlorine is Cl2. So what we're going to do now is we're going to look at the trend in melting point and boiling point of sodium, magnesium and aluminium. So we're going to look at the trend just within those three. So as we go from sodium to magnesium to aluminium, we go from here to here, the melting points and boiling points increase. Okay, to understand that, we're going to look at the structure. Let's start off with aluminium. So what we've got here is we've got an Al3 plus ion. So here is an Al3 plus ion. It has to be 3 plus because it's in group 3 of the periodic table. You'd have to lose those 3 electrons to give it a full outer shell. So it loses two 3s2 electrons and one 3p1 electron. 3 electrons in total per ion. Let's draw a small structure of aluminium. So we're going to draw a giant metallic structure of aluminium. I'm only going to draw 4 aluminium ions. Okay, now if I'm only going to draw 4 aluminium ions, clearly there'll be millions of these in reality in a piece of aluminium. Then what I need to do is I need to look at that charge there and write down the appropriate number of electrons. So this is Al3 plus, therefore it needs 3 electrons. This one needs 3 electrons, this one and this one as well. That's 4 times 2, that's 12 electrons in total. So I'm going to draw 12 delocalized electrons. There we go. Okay. And similarly, you could draw a similar structure for magnesium if you wish, if you have space. I don't, so I'm just going to draw sodium, and we're just going to compare these two, which is enough because the trend of magnesium will be in between sodium and aluminium. Now, before I start drawing the sodium ions, I need to bear something in mind. I need to bear in mind that the ionic radius, that's basically the measure of how big these ions are, of sodium is greater than aluminium. So we can see here that I've drawn the sodium ion bigger than the aluminium ion there. And there's a reason for that. Okay, and the reason for that is that sodium has got more sodium has got less protons than aluminium. Sodium's got less protons than aluminium. Each sodium ion has only got 11 protons. I'm going to write 11p down there. However, each aluminium ion has got 13 protons. I'm going to write down 13p there. I'll put protons at the end actually. Therefore, if it's only got 11 protons, then those outer shell electrons are not pulled in as tight. If you've got more protons in the nucleus, then you've got a greater force of electrostatic attraction pulling those outer electrons into the nucleus. So the ionic radius is much smaller for aluminium compared to sodium. That's a key difference there. So we need to know why the ionic radius is larger. So I've drawn out a diagram to represent that. Let's not forget as well that this time I've only got a 1 plus charge. I'm still going to draw 4 ions though. Okay, this time I need to write down the appropriate number of delocalized electrons. That's 1 for each of these ions. Just randomly put. And we all know that these are giant metallic structures, and giant metallic structures conduct electricity. And that's because of these free delocalized electrons that are able to move to carry the electrical charge. And often you see these diagrams with arrows on there to represent that. So some key differences here so far. We've got a larger ionic radius and less delocalized electrons and a lower charge. Now we can use this information, the fact that this one here has got a lower charge on the ions, it's got less delocalized electrons and a greater ionic radius, to explain why it's got a lower melting point than aluminium. In fact, at GCSE you might have seen the experiment when you put sodium into water and you see that sodium actually melting into a ball on the surface of the water. Aluminium would need a much higher temperature for that to happen. So, let's now explain why sodium has got a lower melting point than aluminium, or why aluminium has got a higher melting point than sodium. And we could do the same thing for magnesium and sodium, or magnesium and aluminium. We could do any comparison here. So, let's look at why aluminium has got the highest melting point out of those three. Well, the first reason, if we look at this image here, is that we've got a higher charge on the ion. So we explain why aluminium has got a higher melting point. Al has a higher melting point. I'm going to write down the reasons here. So the first reason is it's got higher charge on the ion. That's our first reason. The second reason is that there are more delocalized electrons. Number 3 is that the ionic radius is smaller. Okay, so to answer the question why these 3 factors are important in making sure that aluminium has got a higher melting point. Well, if you've got a higher 3+ charge on the ion, then the higher the charge, the more the electrostatic attraction between the ions and the delocalized electrons. The more delocalized electrons you've got, the second point, then the higher attraction between the delocalized electrons than the ion. Number 3, the ionic radius is smaller. Well, what that does is that gives a higher charge density. Charge density is how much charge something's got for its size. So aluminium has got a higher charge density. Therefore, there's more electrostatic attraction between the ions and the delocalized electrons. So these 3 factors here increase the electrostatic attraction between the positive metal ions and the negative delocalized electrons. So these factors increase the electrostatic attraction between the positive metal ions and the delocalized electrons. So we've now explained the trend within sodium, magnesium and aluminium. Silicon has got the highest melting point out of all of these elements. So silicon has got the highest melting point and boiling point out of all period 3 elements. And there's a reason for that. The reason for that is due to its structure. It's got a giant covalent structure. Let's think about this. Silicon is in group 4 of the periodic table. It's in period 3, but it's in group 4. 1, 2, 3, 4. Therefore it has 4 electrons in the last shell. If it has 4 electrons in the last shell, then it has 4 bonds going to it. It's 1, 2. Notice those 2 bonds there are in the plane of the paper because there's no dashes or wedge used. With a wedge coming out of the paper, you'll have seen that wedge in topic 3 bonding, and a dash going into the paper. Again, you'll have seen that in topic 3. This has got a tetrahedral structure. Now, each of those bonds is chemically bonded to a silicon. Each of those silicons are bonded to 4 silicons. That's 1, another 1, another 1, and another 1. All of these are bonded to 4. Those atoms that are bonded to these ones are also bonded to 4. So therefore this only shows part of the structure. So this is only showing part of the structure. You'd have 3 more bonds coming off of each of these to form a giant covalent structure. Now, if you were wanting to melt silicon, or you want to boil silicon, what you would have to do, the only way to do it, would be to break these very strong covalent bonds. And that is going to take a lot of energy. Therefore, silicon has got the highest melting point and boiling point of all period 3 elements. So it has a giant covalent structure. So when silicon is melted or boiled, the very strong covalent bonds between the silicon atoms must be broken. Notice I put quite a few keywords in there. You'd be surprised at how many marks you would get for this particular question. So some keywords the examiner is going to be looking at is giant, that's 1, covalent. Now it's not good enough just to say covalent structure, because chlorine's got a covalent structure. It's got a very low melting point and boiling point. The key thing here is giant. So there's lots and lots of covalent bonds that need to be broken. So it has a giant covalent structure, so when silicon is melted or boiled, the very strong covalent bonds between the silicon atoms must be broken. And if there was only just one of them, then one bond that need to be broken, then obviously silicon would have not quite as high melting point and boiling point. But the fact that there are millions of these silicon covalent bonds that need to be broken. So it requires a lot of energy. So there are lots of silicon bonds need to be broken, so it requires a lot of energy. Okay, and you would have answered a very similar question at GCSE of why diamond has got a high melting point and boiling point. All we've done here is we've just built on that knowledge and we've applied it to silicon. So we're looking at a period 3 element rather than a period 2 element like carbon in the form of diamond or graphite. So what have we done so far? We've done sodium, magnesium and aluminium. We know that there's a general increase in boiling point and melting point from sodium to magnesium to aluminium. We know that then there's a rapid increase even further to silicon. What we're going to do now is we're going to have a look at these three elements here, these ones. So we're going to look at phosphorus, sulfur, and chlorine. And to answer that question, I'm actually going to draw a phosphorus molecule, a sulfur molecule, and a chlorine molecule. So the first one I'm going to look at is phosphorus. Now phosphorus is actually P4, which means there are 4 atoms in a molecule of phosphorus. Now phosphorus, if you look at its position in the periodic table, so do that now, is in group 5. Because phosphorus is in group 5, it needs 3 more electrons for a full shell. So that's 5, 6, 7, 8. 8 electrons in total to give it a full shell. So that means each phosphorus atom must be bonded to 3 others. So let's draw my 4 phosphorus atoms. And each one of these needs to be bonded to 3 others. Let's start with this one then. Watch this. 1, 2, 3. Let's do this one now. 1, 2, 3. And this one. 1, 2, 3. Let's double check that one. 1, 2, 3. So it actually gets this sort of structure here. Now these bonds don't actually cross. The whole thing, if I was to draw this 3D, if you can imagine this, the whole thing is actually, if you imagine the tips of my fingers are the phosphorus atoms, the whole thing is kind of twisted like that, okay? Where each phosphorus is bonded to 3 others. So there's a molecule there with 4 phosphorus atoms covalently bonded together by covalent bonds. It's still a simple covalent molecule though. 4 atoms isn't millions. It's still a small, simple covalent molecule. Next one is sulfur. Now sulfur is an interesting structure. It actually forms rings of 8 atoms. Rings of 8. And that must be correct because each sulfur atom is bonded to 2 others. And that's because it needs 2 more electrons to give it a full shell. That's because it's in group 6, just below oxygen in the periodic table. So oxygen needs 2 more electrons, and sulfur needs 2 more electrons. Oxygen obviously does it in a different way. Oxygen forms an O2 molecule with an O double bond O. However, sulfur does it in the form of a ring of 8. Like if you look at phosphorus here, which is in group 5, if you look at the element above phosphorus in the periodic table in period 2, you'd find that as nitrogen. Now you know from GCSE that nitrogen is nitrogen, triple bond nitrogen. So it's an N, triple bond N. It needs 3 more electrons to fill the shell. This phosphorus also needs 3 more electrons to fill the shell, but it does it in a different way. Okay, so that's the structure of phosphorus, that's the structure of sulfur. The next one on the periodic table you have come across before, and that is chlorine. And you will know from your group 7 work at GCSE that chlorine forms diatomic molecules. So that's Cl2, like that. Okay, again with a covalent bond in there. Now these three here represent the simple molecular structures. If you want to, we can sneak that one on the end there. We've got a little bit of space, so let's do that. Now argon is a noble gas. It's got a full outer shell, does not need any more electrons to fill the shell, therefore it does not form covalent bonds. Okay, so they're just Ar atoms. Just like that. Okay. Now, what we now need to do is we're going to draw another molecule of each one of these next to it, so we can describe the intermolecular forces of attraction between these molecules. Okay. This one has the lowest intermolecular force of attraction between these two atoms. Remember, these are not molecules because there's only one atom there. These are molecules, these are atoms. When you're describing your answers, make sure you use the correct terms. It's not only useful to describe the trend, but you must use the correct language. These are atoms, these are molecules. So the force of attraction between these atoms is quite weak. I'm only going to draw a very thin dotted line there. Now there's three types of intermolecular forces of attraction that you learned in topic 3. They are, in order of strength, starting with the strongest, hydrogen bonding, permanent dipole-dipole, and van der Waals. All of these, of course, are van der Waals. They cannot be hydrogen bonds because you haven't got a highly electronegative atom, such as nitrogen, oxygen, or fluorine, directly chemically bonded to hydrogen. They cannot be permanent dipole-dipole because these molecules here have no overall dipole. So it has to be van der Waals, that's all. So this one here has got the weakest one. So this has the lowest number of electrons. Argon has the lowest number of electrons. Cl2 has a few more electrons. P4 has even more electrons still. And S8 has the most electrons out of these molecules and that atom there. The more electrons you've got, the greater the van der Waals force of attraction. The greater the van der Waals force of attraction, the more energy is needed to overcome that van der Waals force of attraction to melt it or boil it. The more energy is needed to melt or boil these substances, the higher the melting point or boiling point. So the melting point and boiling point is all to do with the strength of the intermolecular forces between these molecules or atoms. So we've got a slightly greater intermolecular force of attraction between these molecules. A greater force of attraction still, and an even greater force of attraction there. So let's compare these 4, starting with the highest melting point and boiling point. So this one here is the first. It's not the first one within period 3, but it's the first one out of these 4. So first, second, third, and fourth. Let's get a very brief explanation down. Please, I'd like you to do this in full sentences. I'm just going to write the main bullet points down. The smaller the molecule or atom, the lower the intermolecular force of attraction between the molecules or atoms in this case for argon. The less energy required to overcome this force of attraction, therefore the lower the boiling point or melting point. So we have a trend here. Okay, what we're going to do now is I'm actually going to write down the actual melting points of all the elements in period 3. So now we measure things in Kelvin normally. When you're watching the weather forecast, then in this current we use degrees Celsius, but we measure temperature in Kelvin in science. So the lowest, okay, so the lowest one out of all of these is argon, and that has got a melting point of 84 Kelvin. 84 Kelvin. Now, the next one is 172 Kelvin. That is chlorine. And the one after that is 317. And then you've got sodium, which is 371. And then it's sulfur, which is 392. And then magnesium is 922. You don't need to know these, but you do need to know the trend. And of course, aluminium, it's got a greater charge density, it's got a higher charge, smaller ionic radius, more delocalized electrons. It's going to be higher than this value, so that's 933 Kelvin. And then silicon's huge, it's 1683. Okay, now writing the data out like this isn't that clear, so what I'd like to do now is I'm going to sketch a little graph. I'm not going to put any axes on this graph. I'm going to put axes on rather. I'm not going to put a scale on this graph, but I'm going to sketch it out. So I'm going to sketch out the melting points of these elements in period 3. So along this axis here, I'm going to have the elements. So we've got sodium, magnesium, aluminium, silicon, phosphorus, sulfur, chlorine and argon on the side there, like that. And up the side here, we're going to have the temperature in the melting point. So the highest, of course, is silicon. So let's put silicon up here. That's the highest. Then we've got sodium, magnesium a bit higher than sodium, aluminium higher still. So there's a trend here, an increase from that one to that one to that one. And that increase here is explained here to there. This one, I'm not going to connect it to any other ones here because we've explained that on its own in this space here. Then let's make sure we get these the right way around. So argon has got the lowest. Let's put this one right down there. Chlorine is a tiny bit higher than argon. Then it's not sulfur. It's phosphorus. And then it's sulfur. So this trend is like that. Okay. So there are 3 separate explanations. There's this description for those 3 elements. This one to explain why it's the greatest. And then these ones. Okay. And we can relate all of that back to the type of bonding in the elements. Right the way back there.